Hello students, to this massive open online course on advanced analytical technique, and we are on the verge of finishing of this course and we are already entered week 12, and today we are going to cover the whole topic and we will also look different optimizations with regard to the high performance liquid chromatography. We have already discussed the basic instrumentation. We have also discussed the detectors used in HPLC, and we have also explored the columns frequently used in HPLC. We have also explored certain practical issues, practical problems, and also the resolutions also, that how we are going to resolve the particular problem. And now it's time to further look into certain optimizations with regard to HPLC. So initially we have to look that what are the factors which we have to account while selecting a particular column for a particular separation process. So we have to look few important points. For example, initially we have to look that what type of analyte, that is what type of mixture we have to separate. Type means that we have to look into the chemistry, into the important aspect that whether we are going to separate a polar analyte or whether we are going to separate some non-polar solutes by using HPLC, or is there some ionic compound, or it may be some biological sample, or it may be a synthetic polymer. So depending upon the nature of the analyte which is to separate, we have to select the column. Then after ensuring the nature of the analyte, we have to look for that what type of sensitivity is required. So we have to look for sensitivity, that is how much sample is there through output, that is whether we are having a few ml of separation or we are having liters of separation. On that basis we have to decide the column. So it may be some a closed column or it may be some open tubular column, depending upon that how much amount is needed to be separated. And also accordingly we have to see that how much pressure is needed for the mobile phase to pass through that packed column. Similarly, we have to look for the matrix, that which type of stationary phase we have to choose, and on the basis of the interaction of the analyte with regard to the stationary phase. So we have to choose the stationary phase accordingly, and then the most importantly we have to select the detector, whether we have to use detector, for example UV visible detector, or whether we have to look for certain refractive index detector, depending upon that which type of actually sample is there. Similarly, if certain you can say that with regard to structure elucidation is required, then we go for the mass spectrometer. Similarly, if there are some chromophore there, then we are using that detector which is going to detect that chromophoric agent. So depending upon the nature of the analyte and our requirement of separation, we have to decide the detectors also. So we have also seen that selectivity is very important. Similarly, retention factor, that retention factor is the is the most basic quantity of any separation, or on the basis of retention factor we actually decides that okay, there are three different TRs are coming, three different retention factors are coming, that actually signifies the number of possible analytes present in that given mixture. Similarly, we have to decide the efficiency, that how much long column is desired, because the efficiency is directly linked to the length of the column. So the moment a separation is required, we have to decide that how much long column is required, because the longer the column, the greater will be the number of theoretical plates in it, and these theoretical plates are purely an imaginary concept. We have discussed a lot about these, and all the time we have also given you a caution that these are theoretical plates, these are imaginary plates present in a column. Practically there is no plate inside the column. The column is actually hollow with a stationary phase in it. Okay, so the efficiency is decided with regard to the number of theoretical plates a particular column has had. but at the same time there is a trade-off between the length of the column and the time of run, because the moment you start increasing the length of the column, okay, efficiency is also increasing, but at the same time the run time, that is the time taken by your column to separate different components of your sample, also increases. So you have to check that whether by increasing the efficiency, whether you are compromising with time, that is you are taking too much time or not. So you have to look for the trade-off between the efficiency and time. HETP, that is the height equivalent to theoretical plate. And also for the back pressure. Back pressure is always there, and this back pressure can be minimized by taking small particles. Okay, so we have already looked all these factors. We have discussed all these factors when we were discussing the elution chromatography, when we were discussing the gas chromatography, and also we have discussed it with regard to the HPLC. Now there are certain equations. The most commonly used equation is the equation used to calculate the retention time, that is given by TR minus T naught upon T naught. TR is the time taken by your analyte to elute, or you can say the time taken by the analyte from column to detector. Okay, that is called the TR, and this T naught is the void time, or you can say dead time. Now let me draw another chromatogram. For example, here it is. Then if you are having a separation of a single component like this, then if you drop a perpendicular, then this time, and moreover you have another peak, let me call it, this peak is called as T naught, sometime this peak is also called as Tm, and this distance is the T naught m, and this distance, half of this, is called as the TR. This is the response time here, response time on the x-axis, and here you have on the y-axis you have the detector response. So this T naught is also called as the void time, dead time. This is the time taken by the mobile phase alone. Okay, that is, it is the time taken by the mobile phase without having any interaction with the stationary phase. So here we have defined this TR minus T naught upon T naught. Similarly, in order to calculate the number of theoretical plates, we have this equation, and we have also solved certain examples by using this equation, that is called as the efficiency may be defined as 16 into TR upon W is the width of the peak at baseline whole square. So we will be using these equations in the later part of this lecture to solve few problems again. So when we have to, stationary phase chemistry is very important, because it is the stationary phase on which different solute molecules of your sample interact, and on the basis of the strength of interaction they have different migration rates, and on the basis of different migration rates they elute at different times, that is they have different TRs, and each TR actually represents the interaction of that particular component with the stationary phase. So it is very important to know the stationary phase chemistry, and we have to judiciously choose the stationary phase so that we can actually tailor, we can actually have a good interaction of different solutes with our stationary phase. So let us explore some of the commonly used stationary phase, and with respect to their polarity, with respect to their selectivity, with respect to their different interactions. So let us start with a non-polar, most commonly used C18 phase. That is, C18 means bearing 18 carbon, or it may be called as, that is, octa octadecyl. Okay, octadecyl, that is C8 carbon. It is a non-polar stationary phase, and this non-polar stationary phase is exclusively used in reverse phase HPLC. In reverse phase HPLC, we use this C18, sometimes C8 also, and as a stationary phase, and there we use polar mobile phase in the reverse phase HPLC, and we have already discussed this in the previous lectures. So here this is you called as the universal stationary phase, because you can use it to separate a large number of compounds. You can separate a large number of compounds, maybe organic or inorganic compounds. Sometimes you can do certain chemical reactions, you can do certain chemical alterations, and you can also induce certain polar groups. Okay, so you can actually make it little moderately polar also. Okay, now C8 has, it is used for less hydrophobic analytes, and it actually it gives you lesser retention times. Okay, so you can also use C8 depending upon the type of analyte which is to be separated. Similarly, you have this phenyl, that is pentafluorophenyl groups. So the moment you induce certain polar groups, then of course, because of the presence of phenyl group, because of the induction of this phenyl group, that is this group, because of the induction of this group, now actually you have the pi-pi interaction, and now it is more suitable for those compounds which can interact with this pi-pi interaction. So you have actually tailored your stationary phase with regard to the nature of the analyte which is to be separated. Similarly, you can also induct cyano groups, and the moment you induct cyano group, your stationary phase becomes good for separation with regard to the normal phase HPLC, as well as the reverse phase HPLC. Now you have actually induced selectivity in your stationary phase. Similarly, you have another very important, that is HILIC phase, that is called as the hydrophilic interaction liquid chromatography. Here actually these stationary phases are very polar in nature, and you can separate a large number of polar compounds, and particularly you can separate sugars, you can separate certain polar compounds. So this is very important, and you actually induces certain amide groups and certain zwitterionic species to impart polarity. Okay. Similarly, you have ion exchange, where you actually ion exchange stationary phase gives high selectivity for the separation of amino acids which have a charge difference, which have a pole, a positive pole, that is a cationic end, and a negative pole, that is an anionic end. So because of the separation of charges, ion exchange chromatography is very good for separation of the compounds which have dipoles. Similarly, the size exclusion chromatography. This size exclusion chromatography actually works with regard to the separation on the basis of the size. So these size exclusion stationary phases actually contain certain porous material or porous stationary phases, where the different analytes actually go into those cavities and they get separated. So the analytes which are bigger in size, they elute quickly, while those analytes whose size are close to the size of the cavity of the pores of this stationary phase get retained, and after a while they also elute. So here elution, or you can say the retention, is based on the size of the analytes which are to be separated. Okay, so here we have summarized few stationary phases, their advantages and also their disadvantages. So polar embedded C18 reduces Selenol effects for basic analytes. Now what it means actually, that in certain issue cases that we have and because of this presence of this silanol group, it actually imparts acidity, and because of this what happens is the basic group attaches to it and it reduces, or sometime it produces certain unwanted peaks or impurities. So we are going to study this in the coming slides also. Now quickly we have to get a summary of the previous slide. For example, if we have a C18 stationary phase, then of course it is a universal stationary phase, but it is poor for very polar analytes. Okay, so we cannot separate highly polar compounds using this C18 stationary phase. Similarly, if phenyl groups are there, then of course because of the presence of phenyl group, it actually has certain aromatic nature in it, and this gives retention time, more retention time for those compounds which can have pi-pi interaction. Similarly, this is HILIC, which we have already discussed. It retains, it is very good for the separation of polar compounds, but what happens is certain issues are there that it needs very high organic mobile phase for the separation of the polar compounds. In HILIC, sometimes we also use water as the mobile phase. Similarly, ion exchange, here high selectivity ion exchange, because it is the separation occurs on the basis of the difference in charge. So it is very good for the selectivity with regard to the charge, but it requires the buffer mobile phase. pH also creates issues which we are going to see in the coming slides. For example, if we are having a very high pH, then there is a leaching of the stationary phase. So in order to avoid this is only good when we have somewhere the pH ranges somewhere between 2 to 8 or 9. Okay, so column geometry. Now here we are going to study the effect with regard to the length of the column, with regard to the internal diameter, that is here, and the particle size. So we know that the moment we increase the length of a column, the efficiency increases. We have already dwelled on it, we have discussed this, and because of the high efficiency, the resolution is always very good. Always in such cases RS is always greater than 1.5. But the analysis time also increases because now the mobile phase will take too much time. Okay, and at the same time, because of the increase of the length of the column, the back pressure also increases. So these things are good, that you are making your column long to get a good efficiency, to get a better resolution, but at the same time you have to compromise with the time, as well as you have to check for the back pressure. Similarly, the internal diameter. If the internal diameter is narrow, for example here, if it is ranges from 1 to 2.1 millimeter, then of course you have a very good sensitivity, you have a very good resolution of your peaks, but at the same time, because of the small aperture, because of the small diameter, you cannot analyze your sample in big amounts. So you have to always use lesser solvent. Similarly, if you increase the internal diameter too much, that is, you have increased the loading, but at the same time the sensitivity as well as the resolution will be compromised. Similarly, the particle diameter, and we know that the smaller the particle, better will be the efficiency, but at the same time the pressure also increases, and the pressure is inversely proportional to square of the diameter of the particle. Okay, so you have to look for the appropriate particle size. Similarly, a typical HPLC has a length of 250 millimeter with an internal diameter of 4.6 millimeter. So 250 is the length of the column, 250 millimeter, this one, and 4.6 is the internal diameter. Similarly, if you want to have a faster analysis, faster runs, then you can use a small length column up to a 150 millimeter with an internal diameter of 4.6. Similarly, nowadays, for example, in UHPLC, that is the ultra high performance liquid chromatography, the particle size is less, so that we can have effective separation. But at the same time, as we have already said, that you always have to look for the back pressure in case of small particles. So we have seen that the flow is actually directly proportional to the square of the internal diameter, and we have to keep, or we have to have a uniform velocity, or you can say optimum velocity. So if you have to have a high resolution, then the recommended length of the column is somewhere between 150 to 250 millimeter, and the recommended internal diameter is 4.6 millimeter, and the particle size of the stationary phase of the column, which is in the column, should be somewhere between 3 to 5 micrometer. But in LCMS, that is the liquid chromatography mass spectrometry or fast liquid chromatographic separations, we use comparatively shorter columns up to 100 millimeter and a small internal diameter. Similarly, the particle size is also small here. While in the preparative TLC, where we have to separate large quantity of sample, in case of preparative TLC, then you can see that the internal diameter is up to 50 millimeter. That is actually 10 times that used in the HPLC, in the traditional HPLC. And here also you can see the particle size, it has also increased. We can take a particle size up to 50 micrometer. So depending upon the type of separation, we have to fix our column, we have to fix our stationary phase, and accordingly we have to look for the resolution, we have to look for the retention times, run times, and the length of the column. So packing morphology. Now we can have different type of particles of the stationary phase. Now each particle has certain issues, certain good things, certain disadvantages. Now if we are using a fully porous particle, that is called as the FPP, it is the traditional type of particle. It has very good surface area and it is very small size, and because of the small size, the efficiency is very high. But at the same time, you will have to apply a very high pressure, sometimes up to 10,000 psi, so that you can actually put pressure so that your mobile phase can pass through the column, which is highly and tightly packed. Similarly, with regard to the superficially porous particle, now those superficially porous particle have a core inside, they have a solid core inside, and they have a porous shell outside of few micrometers. So these type of particles are used in UHPLC, and of course they have lower back pressure. Since their particles are small, so the eddy diffusion, which is represented by the A term in the Van Demeter equation, that was H is equal to A plus B upon U plus Cu. So eddy diffusion can also be minimized, as well as the B term, that is the longitudinal diffusion, is also be minimized by taking uniform particles or core shell particles. Now if you take monolithic columns, then we know that these columns, these are called as columns because they are very rod shaped particles and because of their shape, they experience very low back pressure, and they are very good for the separation of large biomolecules, for the separation of, you can say, proteins, for the separation of vitamins, and because of the lower back pressure, you can have steady flows. Now again, for core shell particle, efficiency is very good, but at the same time, pressure is an issue. So if you are taking subatomic particles, then you actually experience large pressure, and older HPLC systems were using these type of particles. But if you are using the monolithic columns, then these columns are ideal for the separation of proteins, peptides and other biomolecules, but they have lower surface area. Okay, and because of that you can have a very good separation also. Now stationary phase bonding, end capping and pH stability. So now what does end capping means actually? End capping, what happens that in certain stationary phase some residual SiOH groups remains. That is called as the residual SiOH or silanol groups. And these silanol groups actually, because they have some acidic character, they interact with certain bases if present in the analyte. And because of this, we have to remove these, and we can remove these groups by a technique which is called as the end capping, where we treat our stationary phase with certain groups which actually removes this SiOH bonding, and we get simply sometimes we get this type of substituted bonds instead of SiOH bonds. So in the silica bonded phases there are always chances of presence of silanol groups. These are called as the silanol groups. So these silanol groups are actually not good for our column, because sometimes it also leads to choking of the column. So at extreme pH, now this we have already given you a small idea in the previous slide, that at extreme pH, that is if the pH is greater than 9, or you can say 9 or 10, then what happens is the silica starts dissolving, and this silica, which is actually a stationary phase here, it starts dissolving and it starts eluting with the sample, and this is sometimes also referred as column bleed. Column bleed or column bleeding happens. That is the dissolving of the stationary phase because of the temperature or because of the pH. Here it is actually the pH which is actually destabilizing your stationary phase. Similarly, end capping, it is because of the residual presence of the residual SiOH or silanol groups, and it actually alters the peak shape. So in every case you have to do certain chemical modifications, you have to do certain chemical reactions so that SiOH groups can be completely eliminated. Okay, so that you can have very good improved peaks. Okay, otherwise these SiOH groups will start interacting with the analytes, and if some basic analyte is there, then they are going to clog the column also. Sometimes you have to use the polymeric stationary phases, for example the divinyl benzene, for example you can use certain hydroxy based resins. They have a wider pH range, so sometimes you can use pH from 1 to 14 also, extreme pH. So silica dissolution at high pH leads to ghost peak, and it leads to column choking or column damage. So you have to use highly stable silica beads, and in order to avoid the silanol you have to carry out certain reactions so that SiOH groups can be removed, so that instead of this you replace it with like this, or maybe phenyl, but at the same time you have to look for the analyte nature. Now pore size and the surface area match to molecule size. Now a small molecule which have a molecular mass of less than 1000, they need actually pores ranging from 60 to 120 angstrom here. But for peptides we know that they have a very high molecular weight, sometimes greater than 1000. They need large pores, okay, so that proper mass transfer can occur. Now the important thing that you have two extreme conditions, the small pores and the large pores. Now if there are two small pores in your stationary phase, then the large molecule, they are not going to retain, because because of the large size they are not going to, they are not going to stay in those small pores. So they will elute very quickly and they will have very poor retention time, and this will lead to tailing of your peak. Similarly, if the pore size, if they have very large pore size, then again they have less retention. So you have to have an equilibrium, that you have to select the pores very intelligently so that you can have proper retention and proper resolution. Okay. So column hardware, now you have to look for certain aspects. For examples, you have to use frits so that you can protect your column. Frits are actually, you can say that frits are actually the porous bead type of systems which have pores, and you usually put these frits before the analytical columns so that you can filter out the impurities. And the frits can also help to maintain a constant flow of the mobile phase and the analyte through the column, and they will also protect the stationary phase from the leaching, or they also actually acts as a, so that your column, the stationary phase which is actually in the column, which is pasted in the column, stationary phase cannot be leached out. So by using these frits, you actually have a good flow, thorough flow. You actually protects your stationary phase from leaching or from bleeding. Similarly, if you are not checking your frits regularly, then because of the choking of these small pores, frits are actually very small. Sometimes you use stainless steel frits, sometimes you use the porcelain frits, and they have small pores, and if you are not checking it on a regular basis, then they may be clogged, and the clogged frits give you pressure hikes. Okay, and because of this pressure hikes, you will get distorted peaks like this, and you cannot find the actual issue of these peaks unless and until you look for the frits. So you have to use a correct pore size frit, and generally these frits are located just before the separating column. Similarly, you have to use the ferules. These are certain these frits, these ferules are like this. So like this, these ferules are like this. So they actually make your column leak proof, and they have certain tubing type things so that your column can be leak proof. For example, if in case of if you are having certain mobile phases going on, so there are chances of leakage. So these ferules actually make your column leak proof. Now again, you have to use guard columns. These guard columns are generally placed before the main analytical column. The main aspect of using these guard columns is to protect your column from any impurity, from any suspended particles, and by employing these guard columns, you actually impart longevity to your main analytical columns. And of course, these guard columns are very cheap as compared to main analytical columns. Okay. Similarly, tubing internal diameter and length, so that actually minimize extra column means you have good retention you have good resolutions, and these small IDs are used in UHPLC. Similarly, if you have PTFE, that is polytetrafluoroethylene line tubing, then it can leach to certain plasticizers, and they are very good for the common separation of common organic compounds as well as inorganic compounds. Now back pressure is always there. So you have to, in every case, you have to minimize this back pressure. This back pressure is actually in the opposite of the flow of the mobile phase. So if the mobile phase is flowing this, you will feel a back pressure like this. So this back pressure increases with the column length. Longer the column, higher you will feel the higher you will experience the back pressure. Similarly, the mobile phase viscosity. Higher the mobile phase viscosity, higher will be back pressure. But it is inversely proportional with the particle size squared. So this is actually the good thing. So if your particles are small, then of course you will feel a lot of back pressure. Now this is the proportionality, that is back pressure is directly proportional to eta, L, U is the velocity and dP is the diameter of the particle size. So you can see that it is inversely proportional to the square of the particle size, and it is proportional to the viscosity and also with the flow rate or the mobile phase velocity. So practically you have to understand that how much pressure you need for your mobile phase to pass through the column. For example, if you have a high pressure of 4000 to 6000 psi, pound second per inch. So this is the pressure which generally you experience in your HPLC, that is the traditional HPLC. But in UHPLC, you have this pressure of 15,000 psi, that is very high pressure. So now you have to look for temperature also, because the moment you actually increase the temperature, the viscosity reduces, and this is how you have to interplay with the temperature, viscosity and also the back pressure. Okay, so this is the trading point where you have to optimize your pressure, your retention time and also your particle size. So let us quickly review the checklist for our column. So initially you have to identify the nature of analyte, that which type of analyte you want to separate in terms of its polarity, in terms of its charge, in terms of its size. Similarly, what is your target resolution, and always RS in any case should always be greater than 1.5, and also you have to check that what amount of your sample is there, whether it is in ml or it is in liter or it is more than that. So you have to select the column accordingly. Similarly, you have to look for the pressure, that how much pressure is needed. You have to anticipate the pressure which is needed, and accordingly you have to see that which type of detector is you are using and what are the constraints of that particular detector. For example, if you are using a U visible detector, then you must ensure that you can record the UV absorption. Okay. Similarly, if you are using, for example, refractive index RI detector, then you have to look that whether there is some RI refractive index change with regard to the mobile phase or not. Similarly, you have to choose the stationary phase, whether you are using a reverse phase HPLC or whether you are using a highly you can say a very high polarity stationary phase, or whether you are using the size exclusion chromatography or ion exchange chromatography. So you have to check each time. Now then you have to select the column, you have to look for the geometry, and you have to also ensure the particle size of the stationary phase. Similarly, you have to have one guard column and you have to have frit, so that you can avoid clogging of your column and you can have a good long serving life of your column.